Hello, BC Calculus students. This is Mr. Johnson, and this is section 8.4. And in this section, we're going to take a look at our remaining convergence tests. So we have test number 8, the alternating series test, test number 9, the absolute convergence test, and then test number 10, the ratio test. So we're going to start off by talking about the idea of the alternating series. We know already that most of the series that we've dealt with the exception of possibly the geometric series, is going to be all positive terms. So the first 7 tests, again, except for the geometric series test, all 7 of our first tests are going to be basically reserved for positive series with positive terms. So now we're going to get into what if we have either alternating every other sign series, or possibly a series that would be maybe like a positive term and then maybe a negative term and a negative term and a negative term and then a positive term. So there's some sort of sign change, but it might not be truly alternating. So the first one we're going to get into is a truly alternating series, which means that every other term changes sign from positive to negative. The first one you can see here in the warm-up for part A is the alternating harmonic. You could write this one in terms of a formula as a -1 to the n minus 1 over n. So if n was 1, you get +1. If n is 2, then you get -1/2, and so on, and that would generate that. But we do know that the alternating harmonic is convergent, and we just learned that by definition. However, I'm going to show you the alternating series test, which will prove that. The next one is going to be a little bit different. If we were to come up with the generator for that one, it would be -1 to the n times n over n plus 1. And so you can see by the terms that it is truly alternating. However, if you think a little bit past that, if we were to look at just the limit as n goes to infinity of n divided by n plus 1, it's equal to 1. And so this particular series behaviorally will get closer and closer to looking like -1 plus 1 minus 1 plus 1 minus 1 plus 1, and so on. So this one appears that it would maybe alternate and possibly not converge. But again, our next test is going to be able to analyze a series such as this one. In part C, you can see that we have just a couple examples of just the generic alternating series. And so you may have a generator -1 to the n plus 1. You may have a generator of -1 to the n. You may have a generator of -1 to the n minus 1. And obviously there are other ones beyond that. For example, trigonometry can sometimes produce an alternator. So anyway, what we're dealing with here is alternating series. So if you have an alternating series, you're probably going to look to the alternating series test. If not, you're going to probably look towards possibly the ratio test, which is going to be our final one. So here is the alternating series test. I'll just outline it for you quickly. What I do is I set up a 3-part checklist. So the formal definition is here. Let me just organize how I at least think about this. So number 1, let me change back to red. So number 1, I ask myself, is the series truly alternating? If it's not, we can't use this test. So that would be our first check that we want to look at. The second one, and it says here, let me just highlight what I'm talking about right here. It says b sub n plus 1 is less than or equal to b sub n. That's a fancy way of saying that we have a decreasing series. And actually beyond that, just to make sure to clarify, notice how when we look at b sub n plus 1 less than or equal to b sub n, we're looking at the generator. We're not looking at the alternator. So notice that we're just focused on this generator in the series itself. So in other words, we strip away the alternator and just take a look at the series generator b sub n and determine if that's going to be decreasing or not. If that's decreasing, that check is there. That's the second thing we look for. And then the third thing we look for is the limit as n goes to infinity. And this is again of just b sub n, not the alternator, but just b sub n, and that must be 0. And so if all 3 of those items are in place, then we have a convergent series by the alternating series test. Now let's say, just hypothetically, that we have an alternating series, however, it's not decreasing. Well then, in a situation like that, let's say that it was increasing, for example. It may be the kind of case where it's going to be, instead of decreasing or increasing, it just kind of stays constant. But let's say that it's increasing, but it alternates. that means that we're getting further and further away from a convergent value. So if you're going through this checklist and you identify that it's an alternating series, and then you go to the next one and it's not decreasing, you have a divergent series. Let's say that you have an alternating series that is in fact decreasing, however, the limit is going to be something other than 0. For example, if you look back on letter B above here that I'm highlighting, this one has a limit of 1. It is alternating, it is decreasing, and yet we're going to have a divergent series because of the fact that that limit is not 0. So as the terms alternate, as they decrease, they must have a limit of 0 to guarantee convergence. And again, we'll look at a lot of examples here. Okay, so let's take a look at example 1. And with example 1, we certainly have, if we were to just sort of organize our checklist here, we certainly have an alternator, because if you notice, we have -1 to the n, and that's going to just itself prove that it alternates. Number 2, we're looking for whether or not it decreases. Now, when we look at whether or not a generator decreases, we may be able to do it by observation, which is pretty common. But if you think about it, we're trying to show that b sub n plus 1 is less than or equal to b sub n, which would equate to 3 times n plus 1 divided by 4 times n plus 1 minus 1, and I'm comparing it to the original. So all I'm doing here is I'm taking away the alternator, and I'm taking a look at the original generator right here in green that I'm highlighting. That is going to be b sub n. And so when you think about this inequality, and I guess this is a question mark here, we don't know if it's less than or equal to. That's the question we're trying to ask, and it's a little bit hard on a problem like this by observation. So one of the things that you can do is use the first derivative test to look for either a negative first derivative or a positive first derivative. And we talked about this way back in section 8.2. So if I was to take the derivative in terms of n, I guess we're doing, of 3n over 4n minus 1, I have the low function times the derivative of the high one minus the high one times the derivative of the low divided by the low one squared. And again, remember what we're looking for. We're looking for the sign of this, if there's a distinct sign or not. So we have 12n minus 3 minus 12. I think I missed, all right, go back up here and fix this, please. So this is supposed to be 3n times 4. So we have in the numerator, and I thought I wrote this, but apparently I didn't. So square that denominator. I'm sorry for those errors. So we have the denominator squared. So our numerator is going to simplify to -3 divided by 4n minus 1 squared. And the denominator is always positive, and the numerator is clearly negative. So by the first derivative test, we've shown that the first derivative is negative. So we can, in fact, say or verify that this particular generator is decreasing. From my experience, 9 times out of 10, you can test whether or not it decreases by observation. And you'll see some examples a little bit later on of that. Okay, the third step is that we need to take the limit of that non-alternating generator. So the limit of 3n over 4n minus 1, and that limit is 3/4. Now that is not 0, and that is enough to show divergence, not convergence. So we could say that therefore this particular series diverges. All right, let's look at another example. Really similar here. We have an alternator. So that's our first observation. Alternator, this one happens to be -1 to the n plus 1. It's a little different, but it still alternates. Number 2, we're looking at decreasing. We're going to have to sort of do the same thing here because this one is not too obvious, I don't think, if you were to sort of list out whether or not it was decreasing, just because both the numerator and denominator are changing. What you're going to find is that most of the time when you're analyzing the alternating series test, just the denominator is changing, and it's really easy to see that it's decreasing. So we have low d high minus the high function times the derivative of the low. I'll try not to mess up this time. N cubed plus 1 squared. All right, this time we have in the numerator 2n to the fourth plus 2n minus 3n to the fourth. And we have negative n to the fourth plus 2n. Okay, so again, the denominator is positive. You know, I should have mentioned this in the last one as well, but remember how we're not too concerned. Like there may be a couple values of n which may cause this, you know, back to this blue one as well. There may be a couple values possibly that could cause the first derivative as we test it to be either 0 or negative. Remember with n, we're looking at, like in this case, we're looking at n is starting at 1 and going to infinity, but really what we care about is as n continues to get large, we want to know what the derivative sign is going to be. So let's say that the derivative is positive for n is 1 and n is 2, for example, but then it becomes negative for the rest of the time. That's what we're concerned with. So we're concerned with the fact that the generator is decreasing over time and that it doesn't change back and forth from increasing to decreasing. So in this case, it is going to be less than 0 for most values of n here. And so we can check our second item on the list. Our third item is going to be the limit as n goes to infinity of n squared divided by n cubed plus 1. That is 0. And so we have our three-part checklist. And so what our statement would be, or our conclusion, is therefore the series from n is 1 to infinity of our alternator times n squared over n cubed plus 1 is convergent by the alternating series test. So there you go. We have a couple examples there that are similar, yet the conclusion is different for this comparison because of that limit at the end. Okay, let's move on to the next page. All right, here we have a multiple choice problem from the exam. It says the alternating series test can be used to show convergence of which of the following alternating series. So as you can see, all three of these are alternating, and it's asking for which of the three can the test be used. Okay, so we're not really concerned with is it convergent or not. We're just looking at can the test be used. So number one, is it alternating? That's our first. Yep, all three of them are alternating. So we're done with that. We already have been told based on the problem that these are alternating series. So we've gotten that first step off. The second one is, are they decreasing? Now you can see in this first one that it is not decreasing. Notice that it goes from 4, and remember, strip away the sign, okay? So 4 to 1/9, okay, that's decreasing. Now it's back to 1. That's not decreasing anymore. Then it's to 1 over 81, that's going to be decreasing, and then it's going to increase again. So this is gone because it simply does not decrease through the series. Then for number 2, the b sub n 1 over n that we're looking at, does that decrease? And you know, again, this is what I was mentioning before, is that it's a little bit more obvious when it's a simpler generator. So for example, if you're looking at b sub n plus 1 and you're looking at b sub n is 1 over n, b sub n plus 1 is 1 over n plus 1, and you can see right away that the one on the left is less than the one on the right because you're dividing by more. And so this is in fact decreasing. And you know, if we were to take a look at the limit as n goes to infinity of the generator there, it's going to be 0. So this one is in fact convergent, and we can use that alternating series test. And then the third one, okay, it's alternating. In terms of decreasing, you know, again, we're trying to figure out, does this portion of it decrease? But guess what? What we can do instead of wasting time on that is that we can simply take the limit of this one, since we can sort of observe what's happening, and we get 1/2, which is not 0. So whether or not the thing decreases doesn't really matter. Again, the question says the alternating series test can be used to show convergence. Well, this is not a convergent one because the limit is not 0. So we're looking at just option B for this one. Okay, so that's the alternating series test. We will continue to do more practice as we work through this, but we're going to move on and talk about this is not a convergence test, by the way. This is just a little theorem that goes along with the alternating series test and alternating series in general, and it's called the alternating series estimation theorem. And this can be very complex, so just bear with me while I walk you through it. This is the sum. So that is the sum of a convergent series. So what it's saying is that if the sum of a series satisfies the alternating series checklist. So in other words, if number one, you have an alternating series, check. Number two, you have a decreasing series, check. And number three, the limit as n goes to infinity of b sub n is equal to 0, check. So if those three things check off, you have a convergent alternating series by the alternating series test. If that's the case, then you can estimate the sum. And this is what this theorem says. So there's a couple pieces of this that we have to walk through, and I'm going to give you some examples in addition. But first off, R sub n, as you can see, is the sum of the remaining terms after the first n. And I know that seems really confusing, but I'll try to explain it in just a moment. Number two, you have let's do the S first. The S, which is of course the sum, okay? And this is the infinite series. So in other words, that's the exact sum, which is something that we probably can do very, very little. I mean, again, I mentioned this before that the geometric series, you can actually find the sum, as well as the collapsing sum, you can find the sum, but most convergent series, you cannot find the sum, most of them. So in this case, this sum is the exact sum, but we don't know what that exact sum is. Then we have, let me grab another color, we have S sub n. This is going to be the estimate, okay? So we're going to pick a certain number of terms. Let's say we pick 4 terms. That's going to be an estimate for the sum. It's going to be an approximation for the sum. Okay, so maybe you can jot down that this is an approximation to S. All right, and then B sub 1 is the first neglected term. This is a very strange idea at first, I think. So in other words, if you were to use, let me give you a quick example. I'm not going to take numbers here, but let's say that we have this particular series and it's convergent to S, okay? If I was to take, let's say, a sub 1 plus a sub 2 plus a sub 3, I was to take the sum of the first 3 terms, that would be the third partial sum, okay? And we've talked about partial sums back in section 8.2. So if I was to take a look at the third partial sum, we could hypothetically say that the actual sum is approximately the third partial sum. Now, the more terms that we add, so for example, if I was to use the 18th partial sum, that's the first 18 terms added up, that's going to be closer than the third partial sum with an alternating series. And the reason for that is that as I add terms, I get closer to the infinite set of terms added up. Now that should be intuitive, but again, each of the partial sums are approximately the actual sum. So let's say that I added up the first 3 terms and I got an approximation for the actual sum. The theorem says that if you were to take the actual, which again is usually not doable, and you subtract in my little example here, the approximation by adding a sub 1 plus a sub 2 plus a sub 3, okay? If I take the difference, so if I take the error, so if I subtract these, I'm going to add an absolute value because we don't really care if that's a positive or negative. We're looking at how far off are we. So we're looking at the error that is between the actual and the approximate. This theorem says that it is less than or equal to the first term we don't use. So the first neglected term, which in this case is a sub 4, because I did not use the next term in the particular series. I didn't add a sub 4. That was the first one I did not add. Okay, I'm going to give you a visual of hopefully something that helps you visualize and make some intuitive sense to why this works. Okay, so here's what we're going to do. I'm going to start with just this arbitrary number line. I'm going to put in that the sum is right here, okay? This is the actual sum. All right, now let's just assume, because we need to make this as simple as possible. So let's just assume that this is 0, and I'm going to give you a visual of the first term. So I'm going to let the first term be b sub 1. And b sub 1, let's say the first term is 1, okay? Well, that's fine. So I'm gonna represent b sub 1, the length of that as this section right here, and I'm just starting it at 0 because I want to have some sort of basis for this. But let's say that the sum is right here, whatever that may be. That sum is going to be less than b sub 1. We know that for two reasons. Number one, we know this is an alternating series, and number two, we know that each term decreases from the previous. Okay, so we know that b sub 1 is larger than the actual sum. Okay. Okay, now comes in the alternating piece. So let's say that my first term, just like in the problem or in the definition, my first term has a positive sign. My next term is going to have a negative sign. So let's say that from here, because this is where I am, this is going to be s sub 1. That's going to be my first partial sum. So my first partial sum is simply just the first term. I'm gonna add on the next term, which remember is going to be a negative 1 because whoops, sorry, this is going to be negative b sub 2 because it's alternating. So if b sub 1 is positive, b sub 2 is negative. That's going to represent s sub 2, the second partial sum. I'm going to write that below. So s sub 2 is equal to b sub 1 plus b sub 2. Remember how s sub 1 is simply just the first term. Okay, well, so I'm sitting here at the second partial sum, and now I'm going to take and I'm going to add on b sub 3, which is positive by definition because it's alternating. So here I have s sub 3, and that's the third partial sum. So s sub 3 is b sub 1 plus b sub 2 plus b sub 3. Okay, I'm going to do one more. So I have b sub 4, which remember b sub 4 is going to be a negative a term just because it's alternating. And so now I have s sub 4, and s sub 4 is equal to b sub 1 plus b sub 2 plus b sub 3 plus b sub 4. Okay, what's the purpose of all this? Why are we taking time to think about this? Well, here's the idea. Again, so go back to the definition of our alternating series estimation theorem. So what it says is that if you look at the difference between, so I'm back here in the definition, the difference between the actual, which is S, and the approximate, which is S sub n, it is less than the first discarded term. So let's take a look at the example that I gave you. Okay, so I said let's take the first three terms added up. So I wanted you to take the third partial sum, and if we take the actual minus the third partial sum, it is less than or equal to the first discarded term. Okay, let's highlight this in our picture. So we have the actual minus the approximation. Okay, well, that's going to be right here. Let me choose red. Okay, so that's right here. I'm highlighting this in red. The actual subtracted by the approximation. In other words, the difference between the actual sum and the approximated sum is in red highlighted. It says it's less than or equal to the first discarded term. Well, guess what? Here's the first discarded term, b sub 4. And you can see that the red section that I highlighted for b sub 4 is larger than the actual error. So this statement over here holds true that no matter where you end the approximate sum, the next term that you use must be larger than the actual error. It has to be larger than the actual error. In other words, what you do with an alternating series is as you look at partial sums, you kind of toggle back and forth over the sum. So notice that when we were looking at this particular example, we ended here, then we went over here, and then we went over here, and then we went over here, and notice how we were kind of toggling back, and the sum is right in the middle. That's the sum that we're dealing with. And so we're going back and forth over the sum, and we will do that forever until we get down to the actual sum, which takes an infinite number of terms. So as we toggle back and forth, the first term that we would not use in our partial sum, that first term would be the maximum error that would occur. All right, let's try a couple of these on the next page. All right, so we're going to skip example 4 in this. This is going to cause, I believe, more confusion than help at this point with the alternating series. I meant to exclude this this year, and then I didn't. So let's just move on to example 5, because I want to show you this is confusing enough as it is, this alternating series error bound. And so I want to give you some solid examples from the exam that will help you work towards understanding this. And this will take some time for us. So first off, we have a sub n. A sub n is our generator, and it's very ugly looking. So there's the a sub n, and it says let the series a sub n equal f of x for all real x. In other words, here's what's happening is that the series is equal to a function. So we've talked about this a little bit before, but the series itself is going to approximate a function if you were to look at an infinite number of terms. Okay, it says list the first 4 terms, and this should be a series, by the way. Okay, so we're going to generate the first 4 terms as it's asking in the problem. The way we're going to do that is taking the first n value, which is n is 1, and we're going to substitute it in for n in the 3 spots that you see in the generator. I'm going to show you the very first one. So if n is 1, we have negative 1 to the 1 plus 1 times x to the 2 times 1 divided by 2 times 1 plus 1 factorial. All of that obviously simplifies to a positive x to the second divided by 3 factorial. And so that's going to be our very first term. Now we're going to do that for n is 2, n is 3, and n is 4. So I'm going to pause and do that, and I'll come right back. Okay, so here we have our remaining terms. We have all 4 of the terms, and keep in mind that this is, I guess we could say this is approximately f of x. So remember, f of x would be, if I was to continue this forever, that would be the function that we're defining here, is this infinite series that we're looking at, okay? So it says if the 4th degree, so this is really important, so the 4th degree polynomial is used to approximate f of 1/2, what is the alternating series error bound? So remember, f of 1/2 is impossible to find in this given case because we have an infinite series, which is impossible to complete. So this is going to be our actual. This is impossible, but we're going to estimate it. And the way we're going to estimate it is to use the 4th degree polynomial. Remember, a 4th degree polynomial means that we're looking at the power of 4 as we look at our terms. In other words, the 4th degree polynomial will simply be these first 2 terms added up. So maybe I'll just write it as p equals x squared over 3 factorial minus x to the 4th over 5 factorial. And maybe let's just think about it that way. That's going to be our estimate. Okay, so we're going to take our actual minus p and the absolute value of this. This is going to be our approximation or our estimate. And in the problem, it says that we're looking for that error itself. And by definition here, with the alternating series error bound, this is going to be less than or equal to the first discarded term. Now, the first discarded term, I'm going to highlight in green. It's going to be the term x to the 6th divided by 7 factorial. Now, keep in mind that we are looking at an x value of 1/2. We're told that information in the problem. We're looking at x equal to 1/2. And so we're trying to calculate, and you know what, maybe let me go back here and just change this so that it makes a little bit more sense. We're taking our polynomial and we are substituting in 1/2. So we're taking, and I'll write it over here. So we're taking this polynomial and we're actually going to put in 1/2. We don't need to know this value because this is not the value they're asking for. This is, however, the approximate, but we're looking at basically how much does this particular numeric value differ from the actual. So that would be our approximation, and this approximation is similar to f of 1/2, but it's not exact, clearly, and we want to know how far off is it. So we're going to do the alternating series error bound. It's going to be less than or equal to the first discarded term evaluated at 1/2. And if we were to simplify this, we have 1 divided by 2 to the 6th times 7 factorial, which happens to be option C. So that's one example of the alternating series error bound. Let's go ahead and look at another on the next page. Okay, we have a couple things here that I need to quickly outline. So number one, the problem says the Taylor series. Now you have not seen this term, most of you. This is just a special series, and we will be learning about that in section 8.7. So hold tight on that, okay, because I don't want you to get overly concerned. In fact, just cross that off for a second. You don't even need it. This series for the function of f about x is 0. Okay, so just to make sure we don't get totally lost in the terminology. So this particular series is an approximation for a function f. Now, this language right here is a little bit confusing, and we're going to look at it a lot more coming up, but also it's connected to the ratio test. So I want to make sure just to take, this is sort of a side note here really quickly. I want to make sure that that this makes sense, but also you see it as we begin to study it a little bit more later in the section. So this series is a series for the function f about x is 0, and it converges for all values in between -1 and 1. So here's what's happening, okay? If you were to take a look, for example, at a number line in this problem, and we were to center ourselves at 0. So when it says about x equals 0, that's another way of saying that you're centered at x is 0. So that's where we focus our attention on the function f. And any value in between -1 and 1, so I'm going to highlight that just to show representation. So any value in this interval would mean that the series, which this, remember the series is what we're dealing with in the summation here. So this series right here is a perfect match or a perfect representation for f of x as long as x is in between -1 and 1, including -1 and 1. So if x falls in this little set, this is called the interval of convergence. So if x falls in between or inside the interval of convergence, then the series and the function are aligned. They're equal. If x falls outside of that interval, then they're not aligned. They're not equal. Okay, so let me just again write down a couple pieces of terminology. This is the center. This is the interval of convergence. Okay, and this little bit right here, which I'll talk about with the ratio test, this is called the radius of convergence. And I know I drew it from -1 to 0. It doesn't matter. It could be from 0 to 1. The radius of convergence is always a positive value. So it's the distance from the center to the outside of the interval. Okay. All right. So that's just a little side note. All right. Let's try the problem. So we have, let's see, of the following, which is the smallest number m for which the alternating series error bound guarantees that this is true? So remember, we have f of 1. That's the actual. We subtract p sub 4 of 1. That is the approximate. And it is less than or equal to m. Well, guess what? That's the first neglected term. And our job is to figure out what that first neglected term is, because that's what they're asking us to do here. So let's map this out really quickly. What we have is and you know what, if it's helpful, let me just list a few of the terms. I'm going to pause and do that. Okay, so what I did here was that I looked at the first 5 terms. So I did what we did on the previous problem, where I just plugged in k is equal to 1, and I figured out that the first term was -x/3. I plugged in k as 2, figured out that the next term is x²/7, and so on. This set right here, these 4 terms, would be representative of p sub 4 of x. Okay, so that's going to be the approximate equation that we're utilizing. So we would take that ultimately and substitute in 1. This is going to be the first neglected term. In other words, m is equal to, and again, keep in mind that we don't care about the alternating sign. So m is equal to x, which is 1 to the 5th, divided by 31. by the alternating series error-bound theorem. And of course, that simplifies to 1 over 31, and that's going to be option C. So in other words, the approximate is the off of the actual by no more than 1 over 31. All right, that's going to be our first video for section 8.4. The next video will get into the next convergence test. Thank you.